Wear debris analysis compared with spectrographic analysis. The majority of oil samples from machinery are analysed and monitored by spectrographic analysis. This part of the presentation displays the limitation of spectrographic analysis when compared to wear debris analysis by microscope. Spectrographic analysis induced coupled plasma or rotating disc electrode. Spectrographic analysis is the usual routine method for plant and equipment lubricant condition monitoring. Method principle: induced coupled plasma, a solvent-reduced spray of the oil samples injected for an argon gas ionized plasma torch, creating a high temperature plasma about 8,500 Celsius. Rotating disc electrode, a high voltage discharge arc is applied to a porous carbon disc rotating in a small portion of the oil sample, inducing a plasma-like state. Induced coupled plasma spectrographic working principle. The ICP spectrographic analysis works by the first system, sample introduction. A robot sampler picks up the sample from the test tube. There could be 100 samples in the grid. Pistolic pump pumps it through the nebulizer in the ICP area. Plasma torch excites all the electrons. Ion lenses focus it in the sampling interface. Then in the mass spectrometer, the filters split it up so the detector can see what element's what element, usually to be a detector for every element, and the analysis results. Optical emission spectroscopy using a rotating disc electrode. This is a more manual system with the electrodes loaded into the machine individually. The electrode rotates in the sample cup with the oil. The electrode has been soaked in the oil beforehand for a predetermined time. The electrode supplies the arc to give the plasma. The optics and the diffraction produce the spectrum, and analysis results recorded. Analysis process for both induced coupled plasma and rotating disc electrode spectrographic. As the sample passes through the high energy plasma, electrons from the different elements in the sample become excited. When these excited electrons return to a lower level, they emit the light that is characteristic for each specific element. The emitted light is measured by a detector. This measurement provides a determination of the elements present in the sample. The results typically reported as parts per million, ppm, for each element detected, such as Fe35 or copper 60 ppm. Spectroscopy limitations. Particle size limitation. Both ICP and RDE analysis methods are size limited. They can only vaporize and detect particles up to 10 microns in size. Particles larger than 10 microns cannot be fully detected and are usually invisible to these analysis systems. Engine applications are often well filtered. Wear trends tend to produce smaller particles first, allowing spectrographic analysis to detect and trend abnormal wear. Gear drive and transmission applications wear differently, often producing wear debris larger than 150 microns. Particles larger than 10 microns have too much mass for spectrographic analysis to vaporize and detect. Consequently, spectrographic analysis results may not fully reflect heavy abnormal wear conditions accurately. The following examples indicate the limitations of spectrographic analysis when monitoring transmissions, gear drive and hydraulic applications. The left-hand image's wear particles are sized at 6 to 8 microns. These would be detectable with spectrographic analysis. The right-hand image's particles may not be detected accurately. The images below display 3 concerning abnormal wear modes that could remain undetected for up to 6 months before the metallic wear debris becomes broken down small enough for spectrographic analysis to detect. These samples have been analysed by spectrographic and microscope wear debris analysis. On the left, we can see the above ICP spectrographic analysis results are reasonably normal, but when we check below with the microscope, we detected a bearing spall and steel fatigue, all requiring an oil change. Note how these particles were not detected in the above. On the right-hand side, the spectrographic analysis are reasonably okay, and when we check the oil sample with the microscope, we can see there's heavy bronze wear that requires an oil change, displaying the difference in detection limits between the two. In conclusion, spectrographic instrument particle size detection limit less than 10 microns can miss more serious wear modes. Even where spectroscopy, particle counting and PQ combine, recommendations may not be acted on because there isn't enough information to justify changing procedures. Analysis of oil or grease samples by wear debris analysis by microscope provides information on wear modes, contamination types, far more accurately than methods like ICP or RDE spectroscopy. Wear debris analysis by microscope root causes the reason for the contamination found. Identifying contamination allows proactive steps to remove and prevent recurrence. Wear debris analysis by microscope restores applications to target cleanliness levels significantly faster with fewer unnecessary oil changes when compared to relying upon solely ICP or RDE spectrographic results. Note the three images on the right. Note how the microscope has root caused the haul truck centrifuge cake sample. The top image displays silica crystals. The engine has been dusted. The middle image is the large chunks of white metal embedment layer the silica crystals are abrading from the bearings. The bottom image displays the fine dirt is causing arcing in the engine's bearings, producing these carbonized lubricant particles found in the sample. From the information gained from the microscope work on the centrifuge cake, the recommendation to the equipment owner is to work on seeing if the air filtration can be improved. This analysis displays how new engine oil filtration removes all abnormal wear debris, and the best check for abnormal wear is to analyse the oil filter media or centrifuge cake.